Hi, welcome to our paper 3D Vision and Language Pretraining with Large-Scale Synthetic Data. 3D Vision and Language Pretraining aims to train a model to bridge 3D scenes with natural language, which is important for embodied tasks such as 3D visual grounding, 3D dense captioning, 3D question answering. However, 3D VL is limited by pre-trained dataset, as 3D collection dependence on devices, inherent complexities and increased costs in contrast to 2D images. Existing 3D VL datasets have three limitations. Firstly, limited diversity of 3D vision. One of the largest dataset, ScanScribe, combines multiple existing 3D datasets, but still only contains 1,200 indoor scenes. Secondly, insufficient fine-grained 3D text associations. ScanScribe provides 278,000 descriptions of objects, where only the sentence-level target objects is annotated and ignores the other fine-grained associations between the spatial region and other objects mentioned in the sentence. Thirdly, labor-intensive data collection procedure, such as ScanIt++. The 3D data collection of a real scene needs 30 minutes and annotating requires 1.93 minutes. To address the limitation of existing 3D VL datasets, we propose the dataset SynVL 3D, and our dataset has four advantages. 1. Diverse scene data. Benefit from the capability of the 3D simulator. We collected 10,000 indoor 3D scenes with 108 object categories and provide semantic category, visual high-quality mesh, and fine-grained visual annotation, error-free precision, orientation, and segmentation mask of each object. 2. Rich textual description. We utilize templates, image captioners, and GPT-3 to generate descriptions of objects and obtain more than 1 million descriptions. 3. Multi-grained association. We retrain a distinct identifier for every noun phrase, creating a connection between each identifier and a spatial region. 4. Low collection cost. Based on simulators, we can obtain free 3D scene data, use off-the-shelf models to obtain fine-grained annotations and descriptions with few manual annotations. We also avoid privacy issues compared to real scenes. Then, we can construct more fine-grained pre-training tasks, include objects, relationship prediction, multilevel and view aggregated region word alignment, beyond scene text matching and masked language or object modeling, and our model achieves state-of-the-art performance across 3D VL tasks. Based on our proposed dataset, we propose a novel synthetic pre-training and task-specific fine-tuning pipeline, as shown in the figure. Previous 3D VL pre-training tasks mainly contain masked object or language modeling and scene sentence matching. However, these tasks ignore the fine-grained word region correlations. To address this problem, based on fine-grained annotations in our proposed dataset, we design three novel fine-grained pre-training tasks, including object relationship prediction, multilevel and view aggregated region word alignment. Firstly, previous methods neglect relationship understanding between object pairs, resulting in limitations for downstream, and we introduce object relationship prediction task, which predicting pairwise relationship. Secondly, 3D tasks and operations involve multilevel targets with varying granularity, ranging from object, room, to entire scene. To achieve multilevel alignment, we align regions and words at object, room and scene levels respectively. Thirdly, perspective changes when executing operations, which makes view-aggregated alignment critical. Therefore, we introduce the view-aggregated region word alignment. We rotate the point cloud of a 3D scene to different views and aggregate multi-view information for all objects. To achieve precise alignment between regions and words, we perform region phrase matching besides aligning scene and text descriptions. The final pre-training objective combines the losses from the proxy tasks mentioned earlier. Domain shift in our synthetic dataset and downstream task. Real scene data may hinder the 3D VL task's performance. Vision differences can be observed between the synthesized data, the scanned real data. Besides, the descriptions in our dataset are generated by templates or GPT, which also has a gap with artificially annotated language. Moreover, downstream tasks also involve the use of joint vision language, where this type of domain shift requires a joint adaptation. Therefore, we introduce synthetic to real adaptation with a triple domain discriminator in the fine-tuning. The triple domain discriminator consists of three separate discriminators for vision, language and vision language joint domains. The final fine-tuning objective combines the losses from the specific downstream task and synthetic to real domain adaptation. Our method performed the evaluations on 3D VL downstream task and 5 downstream benchmarks, including NR3D, SR3D Scan Refer, Scan 2 Cap and Scan QA. Our method achieved performance improvement on 5 commonly used 3D vision language evaluation datasets. We conducted the ablation studies on the impact of fine-grained pre-training tasks. The results show the effectiveness of our object relation prediction in understanding object-environment relations in 3D scenes and can improve the performance on 3D VL tasks. Multi-level region word alignment can provide multigranularity alignment on object/room/scene and can enhance model perception in 3D environments. U-aggregated region word alignment focus on viewpoint-based region word alignment seems to enhance adaptability from various perspectives. We also conducted the ablation studies on the impact of synthetic to realistic adaptation. When applying adaptation to the 3D vision domain increases performance for various tasks. 2. Extending adaptation to the language domain further enhances results. 3. Incorporating vision language joint domain adaptation leads to additional improvements. For a more detailed introduction, please refer to our paper, the homepage and open source code. Thank you all.